Gypsum products. Gypsum products, as we all know, are very important in dentistry. These are also called plaster of Paris, right? So I will, very sorry. First of all, introduction. It is a white powdery mineral widely found in nature. And they are mainly white in nature. They have a basic formula, which is calcium, which is calcium sulfate hemihydrate. Sorry, dihydrate, right? This is the formula, right? Gypsum products are supplied as fine hemihydrate powder that are produced by heating ground gypsum particles. I'll explain you everything. First of all, classification. Type 1 impression plaster according to ADS specification number 25, right? So you have to remember ADS specification number also. So type 1 is dental plaster or impression plaster, which is also called soluble plaster. Type 2 dental plaster, model plaster. Type 3 dental stone, hydrocal, class 1 stone. Type 4 dental stone, high strength. Now it is high strength, right? Low expansion, class 2 stone, die stone, or improved stone, which is mainly used for casts, right? Where we require high strength, like in case of crowns or bridges. Type 5 dental stone, high strength, high expansion, right? What are the various uses of gypsum products in dentistry? So as we all know, they are used to making study models for oral and maxillofacial structures, as auxiliary dental material in dental laboratories during fabrication of dental prostheses. As we all know, we have to make casts for lab work, models and casts for wax pattern fabrication in case of removal partial denture, or in case of anything where we are going to restore indirectly, and for gypsum based investments. Like when plaster is mixed with silica, it is known as dental investment, and they are used to form molds into which molten metal is cast, right? In case of byte registration to record centric jaw relations, right? Now production of gypsum product. So this is a gypsum products are produced by calcining calcium sulfate dihydrate. As we here we can see gypsum calcium sulfate dihydrate. This is dihydrate. Now under this temperature, 110 to 130 degrees Celsius, calcining, it forms calcium sulfate hemihydrate, and 130 to 200 degrees Celsius, it forms calcium sulfate hexagonal anhydride, and 200 to 1000 orthorhombic anhydride. You have to remember this. This is very important, right? Alpha and beta hemihydrate based on crystal size, surface area, degree of lattice perfection, right? So depending on the method of calcination, there are two forms, right? Alpha hemihydrate and beta hemihydrate, right? So if there is a heat of 110 degrees Celsius, 110 to 130 degree, it form alpha hemihydrate. And if there is a heat of 120 degrees Celsius and 130 degrees Celsius under the 17 lb per square inch pressure, then it forms, this is opposite. This is for beta hemihydrate and this is for alpha hemihydrate, right? Sorry. Here we go. Right. So modified alpha hemihydrate, that is diastone. Gypsum is calcinated under pressure in 30% calcium chloride solution or in the presence of more than 1% sodium succinate to form diastone, right? After controlled grinding, these powders have an even higher apparent density and yield a stronger set, right? Microscopically, they are cuboidal in shape. Right? This is alpha hemihydrate and this is beta hemihydrate. Now come to alpha hemihydrate produced by wet calcination. This is produced by dry calcination. Set structure is stronger and harder. It is less stronger. Smaller, regularly shaped crystalline particle in the form of rods and prisms. And they are irregularly shaped orthorhombic crystals with capillary pores and irregular shape. They have prismatic and crystalline shape. Require less water for mixing, right? It requires more water for mixing. Now, setting of gypsum product. As we can see, reaction between the gypsum product and water produce solid gypsum, right? Some of the unreacted particles heat, which is equivalent to heat used originally for calcination, right? Here is calcium sulfate hemihydrate. It mixes with water, then it produces calcium sulfate dihydrate and some unreacted calcium sulfate and water particles with heat, right? Now the reaction is exothermic and it's same for all gypsum products, right? It is exothermic because it is releasing heat. The amount of water required to produce a workable mix varies between the products. As evident from the above reaction, not all of the hemihydrate convert into dihydrate. We have some unreacted particles also, right? The highest conversion rate is seen in plaster, right? 90% rate seen in plaster. In type 4 and 5 stone, the dihydrate content is about 4 to 5%. 50%. Type 4 and 5, 50% left. Now, less than 50% dihydrate is present in type 4 and 5, 60% in type 2 dye material, and 90% in type 1 plaster. Right. Now, based on three theories of setting, there are based on these three theories, gypsum sets. So one is colloidal theory, hydration theory, dissolution theory. You doesn't need that much, but you must know about these theories. So colloidal theory, when mixed with water hemihydrate, enter into colloidal state through Sol gel mechanism. And in Sol state, hemihydrate particles are slowly hydrated to form dihydrate, which on consumption of the measured amount of water converted to solid gel. In case of hydration theory, dehydrated plaster particles unite through hydrogen bond with sulfate group to form a set material. And in case of dissolution preparation theory, dissolution of hemihydrate particle in water followed by instant recrystallization into dihydrate, right? Thus the setting reactions, how it occurs. So basically, when hemihydrate is mixed with water to form a fluid workable suspension, then hemihydrate, which is 4 times more soluble in water than dihydrate, right? Because it has half of particles. So hemihydrate dissolves until it forms a saturated solution of calcium and sulfate. This saturated solution is supersaturated with respect to the solubility of dihydrate, precipitation of dihydrate occurs. When there is saturation, then reaction stops. As the dihydrate precipitates, the hemihydrate continues to dissolve. The process proceeds as either new crystals form or further growth occur on the crystals already present until no further dihydrate can precipitate out of solution, right? Until there is formation of dihydrate. After that, it will stop. Then, as we all know, it depends upon the mixing time. So mixing time, the time from addition of powder to the water until the mix is complete. When the moment we add the water in the powder, we have to start mixing, and mechanical mixing time is 20 to 30 seconds. After 20 to 30 seconds, there is formation of sole gel. Then hand spatulation at least a minute, and we can pour the cast, or we can use it generally up to 3 minutes. The time starts from mixing to the point where the consistency is no longer acceptable for the product's intended purpose. So it is generally 3 minutes, which is working time. So when we start mixing up to the usage time. So measurement of setting time, there is loss of gloss method, penetration test, use of Vicat and Gilmore needles. Like let me explain you. Like this is a block, and there is a needle which we use to insert. When needle doesn't make any scratch over it, that means it's set. It is set, right? So these are the Gilmore needles, right? We have to give particular pressure over there, right? And we have to check for the final set also, right? So for that matter, we need particular diameter needle with particular weight, with all the 5 types of plasters, right? So we doesn't need that. Now, it all depends upon water powder ratio. Higher the water powder ratio is, the lower the mixing time, and there is increase in setting time, right? Higher the water powder ratio, decrease number of nuclei per unit volume, setting time is prolonged. Within practical limits, longer and more rapidly the gypsum product is mixed, the shorter is the setting time. As we mix more with more force, with more strokes, then it sets quickly. Solubility of hemihydrate, which is very, very, very important. There is difference in solubility of hemihydrate, and gypsum becomes smaller with increased temperature, which lowers the driving force for forming the dihydrate, thus slowing the setting reaction. We all know there is increase in temperature. If there is increase in temperature, then there is decrease in setting time. Later change in setting time occur between 0 to 50 degree, but increase in temperature after 50 degree cause gradual retardation in setting. You have to remember this, right? As the temperature is 100 degree, no reaction takes place at all. Right, this is the graph. Maximum setting is in between 0 to 50 degrees Celsius. Now, for setting time, when we require more time to for work, that is working time you require, then or you doesn't need any kind of, you need less time for working, then we have accelerator and retarders. So accelerator means those who accelerate setting time. Those who basically accelerate setting, not setting time, accelerate setting. Potassium sulfate more than 2%. Agitated slurry water, sodium chloride 2% of hemihydrate, sodium sulfate 3.4%, borax concentration lower than 0.2 mm. Right? Retarders are borax concentration above 0.2 mm. And if it is lower than 0.1 mm, that is accelerator. More than, then it is a retard. Potassium citrate, sodium chloride 20%, acetate, citrate, tetrates, glue, gelatin, some gums. You have to mug up all the things, right? Now, what is setting expansion, which is very, very important, because setting expansion is something like which will change the dimension of the cast, right? So we have to understand the concept of setting expansion. Setting expansion is more important in case of where we are making indirect restorations, like in case of casting, like we are making mold of something, and if there is setting expansion, then it will decrease the size of the cast. So it is of more importance over there. So expansion occur during changes from hemihydrate to dihydrate, right? So that is your setting expansion. The expansion is linear expansion, right? So normal setting expansion, all gypsum products show a linear expansion, which is 0.05 to 0.5%. This you will get direct question, right? Due to outward thrust of the growing crystals during setting, right? Crystals growing from the nuclei not only intermesh, but also intercept each other during growth. Like something is growing over there, something is growing over there, something is growing over there, something, it will increase pressure towards their self also, towards out thrust also, toward inside also, in between also, right? So this is called linear expansion during setting, right? So you have to remember this. Depending on the composition of gypsum product, the observed linear expansion, this is which I have told you, right? And some books write it 0.5 to 0.05 to 0.5%, right? The volume of dihydrate formed is 7.11% less than equivalent combined volumes of hemihydrate water. You have to remember these expansion rate also and volume also, right? Now, how we control setting expansion? As we lower down the water powder ratio and longer mixing time will increase the setting expansion, right? That means lower water powder ratio means we are increasing less of water. And if there is higher water powder ratio, means less number of nuclei of crystallization per unit volume and less growth interaction between the dihydrate crystal and less outward thrust. So higher water powder ratio means lesser expansion. And if lower water powder ratio, then there is increase in expansion. You can remember this also, right? Now come to hygroscopic expansion. This is normal setting expansion. This is hygroscopic expansion. Now understand the concept. Normal setting expansion, I have already told you. Hygroscopic setting expansion, when a gypsum product is placed underwater, right? That's why it is hygroscopic. Product is placed underwater before the initial set stage. A greater expansion is seen. So this is due to hygroscopic expansion. When expansion begins, externally available water is drawn into pores, forming the setting mass, and this maintains a continuous aqueous phase in which crystal growth takes place freely. Under dry conditions, this additional water is not available, and as expansion occurs, the aqueous phase is mix is reduced to form a film over the growing crystal. It is greater in magnitude than normal setting expansion because external water is available. So it is mainly used to expand some gypsum bonded investments, right? So it is helpful. The hygroscopic setting expansion is a physical phenomenon and is not caused by a chemical reaction because basically water is available and additional water is, if available, then it is drawn into the pores, which I have already told you. So it is not by the chemical reaction, it is by the physical phenomenon, right? Which is not available in case of normal setting expansion because there is particular amount of water available. The hygroscopic expansion obtained during the setting of dental stone lasted about twice than that of normal setting expansion. Obviously, because water is available and it is drawn into the pores, and regularly there are formation of crystals. Now, strength of set gypsum products depend upon effect of water content, wet strength, which is green strength. This strength is determined when water is in excess of that required for hydration of the hemihydrate remains in the test specimen. Dry strength determined when the excess water is removed by the drying. So you have to remember these two terminologies: wet strength, which is also called green strength, because excess water is available. And in case of dry strength, there is no water, excess water is removed. Dry strength may be 2 times more higher than wet strength. Now, most important because we normally use water. So greater the water powder ratio, greater the porosity of the set mass. That means water is greater in greater amount, lesser the dry strength because fewer dihydrate crystals remains per unit volume. In case of high water powder ratio, gives a diametral tensile strength as high as 25% of the corresponding compressive strength, and with low water powder ratio, the diametral tensile strength is less than 10% of the corresponding compressive strength. Right. So in case of type 5, we have highest compressive strength, right? Because water powder ratio is very low. Now come to the manipulation. As we all know, we have already manipulated, but let us discuss. In generally, an increase in mixing time increases strength to a limit that is approximately equivalent to that of the hand mix for 1 minute. More than that, there is delay in setting. If the mixture is overmixed, the gypsum crystal will break up, and finally product will hold a less crystalline interlocking structure. Just try this at home or in your clinic. Just continue mixing after 1 minute. There is reaction will not complete, and there are breaking of crystals. Gypsum crystals will break, and they will the product we have will not get any solid mass. Right? This is due to gypsum crystal breaking of gypsum crystals. The addition of an accelerator or retarder lower both the wet and dry strength of the gypsum product. This is due to the salt added as an adulterant and to the reduction in intercrystalline cohesion. Addition of more chemicals may upset the delicate balance of physical properties. So setting time may be controlled by modest alteration in water powder ratio and spatulation time. Spatulation time must be 1 minute. Now come to different types of gypsum product. Type 1, which is called plaster, impression plaster, composed of plaster of Paris, beta hemihydrate. You will get direct question, or in MCQs you already have that question. To which modifiers have been added to regulate the setting time and setting expansion. The composition is potassium sulfate, retarder is borax, and pigment alizarin red. Water powder ratio, you have to remember 0.5 to 0.6%. Fluidity makes it suitable for making impression of soft tissue in the uncompressed state. Preliminary impression of splinting transfer coping utilized to produce long span implant supported prosthesis. Right. Previously, we used it for face records and all. Then type 2 model plaster, it is usually marketed in natural white color, thus contrasting with stone which are generally colored. Weaker the stone, stronger than type 1 model or laboratory plaster used. Fill a flask in denture construction, study models, mounting model, cast, as we all know. Right. Dental stone, which is type 3, composed of alpha hemihydrate, also known as hydrocal. Minimum 1 hour compressive strength is 20.7 megapascal. You have to remember that. Used mainly for diagnostic cast, working cast, model of partial and full denture and flasking. Now this is high dental stone, high strength, type 4, modified alpha hemihydrate, also known as dye stone. This is resistant to abrasion during wax carving for indirect restoration. As I've already told you, when we are preparing wax pattern for inlay, onlay, crowns, then we have to use it. The average dry surface hardness of type 4 stone is approximately 92 Rockwell hardness. Type 3 stone is 82. You have to remember these two also. These are for making dyes. In making cast, model base strength is more important. Then come to type 5, which is also called high strength, high expansion type 5. Higher compressive strength with lower water powder than type 4. So the setting expansion has been increased from minimum 0.10 to 0.30. The rationale for this increase is that the base metal alloys show casting shrinkage, and hence expansion of the investment is needed as compensation. One should avoid the use of type 5 stone for producing dyes or inlays on those, since the higher expansion may lead to unacceptable tight fit, like there is dimensional change with high expansion. So they are mainly used for investments. There are really strong dye models is where a really strong dye model is needed and aid in combustion for alloys, solidification, shrinkage. In case of implants, counts, bridge dyes, right? You have to remember this chart also. Water powder ratio, setting time, minimum, maximum, 1 hour compressive strength. You have to remember this more importantly. I think that is what is required in your exams.